In-person people, your job every class is make sure I start the recording. You failed me, Rocker. Already.
This should be Clancy's job. I'm not responsible.
Oh, hold on. I got to get my shield on. It should be Clancy's job, actually. Clancy, your job is to remind me to start the recording every time. Okay, so let me share this. All right, and I assume everybody has access to the book now. I did take some excerpts out of the book and bring it into the slides. I don't know if you noticed, but so when I reference stuff, I'll try to reference it in a slide. Hold on. I think this might be cheating, but I'm doing it anyways. I love my Tuesday, Thursday schedule. Because now I have all of my classes in this room because they had us double booked. So my 200 class this morning was in S118, and so was Dr. Locklear's cosmogony class. So we came over here, so I'm just having all my classes here, so I don't have to move. They're just back to back to back, just knock it out, hit the golf course. Perfect. Man, it was hot yesterday. Huh? I played 27 holes in that. And I tell you, I didn't feel bad, but the heat drained you. Because my second nine, I shot a 37, and then my last nine, I shot a 48. I don't shoot 48s. And I didn't feel bad. I just think the body was sapped of its energies. So, okay. So at the end of last class, we started looking at, actually, before I go in any farther, I want to just kind of do a little crash course here on scheme. Because I want to once again prove something true from other classes. So I think we already have this slide, but we'll just put it in here again. So we use memory, ask questions, repetition. All right, and 100% of programming languages have facilities for these things. So in Scheme, memory is done through variables. And in all programming languages is done through variables. Specifically in Scheme, Scheme uses the define keyword. Let's go look at this. I'll actually put it down on this guy. So we're going to look at how do we define variables, how do we ask questions, and then how do we do repetition through functions and recursion is what we'll look at. Because I kind of mentioned last class, I think that even though the modern Scheme language does actually include a loop function, we're not allowed to use it. We have to solve everything recursively. You'll hate me at first, and then you'll love me. Because you know how recursion is like a difficult thing to wrap your mind around for. You will almost have trouble thinking iteratively after this class. And then everything will be good. And then it'll become a viable part of your problem solving. Where you'll think about like, I wonder, is there a recursive way of handling this that would make sense? Where before you kind of would have avoided recursion at all costs if you could. So just kind of trust me on it that it'll be okay. Why can't I make this font bigger? You should be able to. Give me a second. Ooh. Is that doing the top too? Nope. Well, no, it did. Did it? All right. Is that good, too big, too small? That looks pretty solid. Okay. Good, because I can see that right. All right, so we might say define, I think we might have done this last time a little bit, but let's just get the language out in front of us and do our conversion. So I might define A to be the number 5. All right, I mentioned last time scheme is a list-based language. So notice that everything is inside of a list. So this is a function called define. And the way functions are defined, so actually let me just throw this into a slide real quick. Do this. Function calls in scheme. So we have opening parenthesis, we have function name, and then param 1, param 2, ... param x, param n, whatever, something like that. All right, so the first thing in our list is the function name, then any parameters it takes. Usually there's at least one parameter. So like last time we looked at the cars and the cooters, so the car function, so for example, car of 1, 2, 3, this is the function car that takes in a single parameter, which must be a list. So the car of this guy would be 1. So I'm applying this function to this parameter. Make sense? Cons, on the other hand, requires 2 parameters. The element you're consing on, so 5, for example, onto a list. So this would produce the list 5, 1, 2, 3. This guy would just give us the value 1. Make sense? But the important thing, what we're seeing here, is how do functions work in scheme, where the first thing in the list is the name of the function. Then it's the parameters. This guy took 1 parameter, this guy takes 2 parameters. The element we're adding, and then the list we're adding it to. The list function takes in any number of parameters that we want to create into a list. So this will create for us the list 5, 1, 2, 3. So it's kind of a shorthand for cons 5 onto the cons of 1 onto the cons of 2 onto the cons of 3 onto the empty list. So this will cons 3 onto the empty list, giving me the list 3. This will cons 2 onto the list 3, giving me the list 2, 3. This will cons 1 onto the list 2, 3, giving me the list 1, 2, 3. This will cons 5 onto the list 1, 2, 3, giving me the list 5, 1, 2, 3. Easy peasy, right? Gets so much worse. It's gonna be great. Huh? Yeah, yeah. And that's what I'm saying. It will be weird at first, just because you're trying to wrap your mind around this like new thing, and it's so different than what you've done. But once you get into it, I mean, I purposely pick scheme as a language because it's so simple. But in its simplicity, you're forced to like do these things linked together like this in order to accomplish anything. No, I don't know. I think it's a blast. All right. But in any case, so we kind of get the function aspect of this. First element is the function name. Then after that is the parameter stuff. No different than what we've seen before. Just we're calling it as inside of a list instead of having define and then passing it a couple of parameters. All right. So we see out here, I'm defining, here's my variable name, and then here's its value. Value can be anything that's a scheme value, so I can say define B to be the list 1, 2, 3, like this, and then I can say car B, which will give me the 1. Oh, I gotta move this, it's in a very inopportune place. So there's my 1. I can say cooter B, which will give me my list 2, 3. I can say the car of the cooter of B, which will give me my 2. Or I can say the catter of B, which is shorthand for this guy, which will also give me the 2. This is the car of the cooter. But you can only link those things through, I think there's maybe like 6. You can do 6 A's and D's in there until it starts, I think the Earth spins the other direction on its axis. But typically, shorthand would be this. You will almost always use like just 1 extra or 2 extra. Anything beyond that, you might be better off linking them like this, just to kind of give an idea of what you're trying to do. Because it starts becoming a little bit, I don't know, difficult. Oh, I like the cadatter. So this is the cooter of it, which is 2, 3. Then the car of that, which actually will be illegal because the car, well, here. Now it's not illegal. It's got a list in there now. So this would be the cooter of this thing, which would be the list containing the list 2 and then a 3. Then the car of that, which will be the list 2. And then the cooter of that, which will be the empty list. So there's our empty list. Or if I kadar, that'll give me my 2.
Sounds like some sort of pirate language.
Hold on. The cooter. The catter. That'll give me my 2. There we go. All right, so Clancy, you're in charge of all pronunciations. And then Sarah, you're in charge of fixing his pronunciations. Yeah, go ahead.
On the second line,
Yeah.
why do you need the capacity for the parentheses?
Okay, yeah, so this is something called, and this is actually, I'm glad you asked it. This is related. He asked, why didn't I need this guy here? Let's actually talk about what this guy means in the first place. So, Ninja. Oh, whatever, I'm not gonna save this anyways. So let me go back to here. We're gonna call this the quoted lists. So define A as 5 versus define A as 5. This guy here will give me the list containing define, containing A, containing 5. Quoting means mute. Don't try to execute this first thing. Don't treat it as a function call, treat it as a list. So so what I'm doing here is if I leave, my watch is misbehaving. Rocker, you're in charge of misbehaving watches. Everybody's got to remember their roles because I'm going to assign multiple roles by me. So if I do this, for instance, I take that quote off there. Notice it yells at me because it thinks that 1 should be the name of a function. Like, there's not a built-in function named 1. Make sense? Okay, so, but when I put the quote in front of it, it's saying, don't execute any of this, almost like a comment. Okay, don't execute this. So now, this guy in here is part of a list. So he wouldn't be attempted to be executed because he's part of a quoted list. Make sense? Oh, I'm going to keep doing that. I should just save it. There we go. Okay, so that's the whole quoted list thing. But in any case, we see that the cadence here is that you have opening parentheses followed by a function name followed by the parameters. And the way that we define variables, I think the comment in here is pound, or is it this? Call this defining variables. I think that works. Okay. So there's our memory piece there, right? Okay, what about conditionals? All right. What would you guess the syntax for a conditional is? Yeah, it's an if, so it's a list containing if, and then the true expression followed by optionally the false expression. So I could say if less than A10, I can boil down to woot, else I can boil down to LOL. All right, so A is currently 5. Is A less than 10? 5 is less than 10, so I should get a woot out of this. There's my woot. If I change A to 50, now I should get the LOL. So this is my Boolean expression. Actually, sorry. If Boolean expression, then true expression, false expression. So this is my Boolean expression. This is what I'm testing. If that guy boils down to true, do whatever this is, which could be something very complex looking. Right now, it's just saying here's the symbol woot. But you know, it could be parentheses upon parentheses upon parentheses, you know, all sorts of crazy stuff. So this is what I do if it's true. This is what I do if it's false. Make sense? All right, so there's conditionals. Now, if I want to do something some number of times, I probably need to house this inside of a function. Okay, so let's talk about lambda calculus. Lambda expressions. So what is a lambda? Lambda is an unnamed function. That we typically will give a name to through a define statement. So we come in here, functions, define factorial to be a lambda. Now factorial is that's like 5 times 4 times 3 times 2, right? Okay, so how many parameters does the factorial function take? If I say, give me the factorial of 4, did I give you enough information? Yeah, you need one number, right? So lambda takes a parameter list, just like any other function, right? We'll call this guy n. And then we have the body of the lambda. So functions have a parameter list, and then they have a body. Just like in Java, just like in C++, just like in Python, that's what a function is, right? So this is a function named factorial. It takes these things as parameters and then is going to do something to them. I'm kicking it down to multiple lines, but you can put this all in one line if you want, but you'll find the indentation will make life a little bit easier here. Now, how do I calculate factorial? Factorial, if n is 4, it's 4 times 3 times 2 times 1, right? So I could ask a question, if equals n1, then boil down to 1. Else, boil down to times n and factorial of minus n1. So this is n times the factorial of n minus 1. You just have to get used to writing it in these, you know, to say n minus 1, I have to apply the minus function to the value n and 1. Yep. So this one closes that one, this one closes that one, that one, that one, that one, that one. All right, so the factorial function takes in a single parameter. If that value is currently 1, it just boils down to 1. That's my stopping case for the recursion. Otherwise, it boils down to whatever the multiplication function is when applied to the current value of n and whatever is returned by factorial of n minus 1. So that is me defining it. Then if I want to apply it, factorial of 4 should be 4 times 3 times 2 times 1. Okay, so 4 times 3 is 12, times 2 is 24, times 1 is still 24. So it should give me 24. And there's my 24. If I change it to a 5, it should give me, what, a 120? But notice this is function name, parameter. But let me show you this. I'm going to take the lambda expression here, everything but that first part, everything but the define. And I'm going to put that here. And I'm going to apply that to, let's say, a 7. So I'm applying this function. I didn't name it, but that's still a function, isn't it? Doesn't have a name. Doesn't have a name, but it's still a function to this value. Now we will have a bit of an issue here where how do I call an unnamed function from within itself? You can't. That's where you might need to name it. Okay, now we see the reason for associating a variable name with a function. So one gap we want to close here is that when I name a function main, or I name a variable a, I'm accomplishing the same thing. I'm associating a variable name with a value. All we just did here is we added to our vocabulary of potential values to be functions. We've been using them forever, but we've always treated functions as like extra thing, right? Well, you've probably seen some examples. JavaScript uses these a lot. They call them closures or callback functions, where you'll write something, you'll say, well, if something goes wrong, call this extra function, or when it's done, call this extra function. You don't pass in a name, you just pass in a function. Effectively, you pass in a lambda. So we call them callback functions, kind of the language theory official term for it is a closure, but whatever. It's just a function you're passing. You didn't give it a name because it's going to be a one-use type thing. When do we use variable names? When you need to use something more than once, right? In this case, I probably need a variable name because I'm going to use this dude more than once because he is written recursively. Make sense? But I can certainly do this. If I want to replace this, let's just write it so it looks a little cleaner. I'll go ahead and I'll create a lambda that takes an A and a B and boils down to multiply A and B. So there's my lambda, and we'll do 7 and 5 will be my two parameters. So I'm going to pass 7 and 5 into this function. This function that takes two parameters, A and B, and just boils down to those two values multiplied together. 35. Go ahead. Right here. Function calls. You have opening parenthesis, function name, followed by the parameters, followed by the parameters. Maybe this is even a little misleading because this is the function, not necessarily the function name. So your question was, why do I have an extra set before this? It's because this is the call I'm making. I'm applying these two parameters to this function. If I don't have the parenthesis here, all of a sudden I just have listed a function here and I just have two values kind of hanging out. Nothing's containing them into like, what do you want to do? All right, that makes sense? All right, So something that you'll see in the book, I'll just kind of mention it here, is functions or lambdas are considered first-class objects. This really means is they are considered values just like any other value in Scheme is. So the value 5 and this lambda that takes in 2 parameters and multiplies them together are just as good as each other. They are considered Scheme values. One is a number, the other one is a lambda, an unnamed function. And we can choose to link them to a variable name if we'd like, but we don't have to. All right, so far so good. All right, so you might say if you want to do something kind of loopy, unintended. So you want to do something loopy, you might say define repeat to be a lambda that takes in a value and a number of times. And maybe what it does is it says, let's say I pass this guy, I'll just pretend I'm calling it here, down here. So I'll say repeat LOL 10 times. Actually, let me do it 3 times just for right now. This should give me the list, LOL, LOL, LOL. I wanted to do something 3 times in this case, produce that, that value 3 times. Make sense? So I'll ask the question, if equal number of times, well, let me ask you this. I'm going to pause this for a second. I'll just leave it at that. We're going to do a little audience participation. Okay, so ultimately I want to have a function called repeat that I pass the what to, and I want that guy to be duplicated this number of times. So if this was my thing, it would be LOL, LOL, LOL would be my output. Okay, what am I actually building here? What's that guy called? A list. How do we build lists? What are my options for building lists? Okay, well, coulders produce the result, a resulting list, but for constructing lists, we use cons, get a cons construct, or we can use lists to build a list. But cons, let's think of that as our primitive list builder, okay? So if I were to build the list, LOL, LOL, LOL using cons, what would that look like? Cons LOL onto cons of LOL onto cons LOL onto empty list. That, right? All right. And I did this 3 times. Cons is called 3 times here until we finally get to the last time where we finish off the cons with an empty list. I need to finish with an empty list because cons requires the second parameter be an empty list. Okay? So with this being the case, take a couple minutes and write that repeat function based on what you've learned so far. to change that reminder. Golf tea time pops up in the middle of class. I had a summer schedule, people. All the online people have their cameras off, so you can't tell whether or not they're taking the dog out.
I already don't notice.
Oh, there's Clancy.
That is the recursive guy that we love. No one loves recursive.
By the way, no, I did get your text message. It seems like I must have let you in, or it automatically let you in or something.
I changed the way that I sign in.
Oh.
Then it let me in.
Yeah, actually, maybe that's it. If you sign in, if you're logged into your CUW account and then you join, it goes ahead and assumes that you're not one of these class bomber people, or you come in and start cussing and stuff. So that actually gives you quite a bit of power. It was somebody with a CUW.edu email address. Gotta be careful of these disgruntled students, right? All right. All right, so let's take a look at this. So we're gonna take in our value and then the number of times we want it to repeat. We're gonna ask the question, if equals number of times is 0, we're gonna boil down to the empty list. Otherwise, we're going to cons val onto repeat of val and minus number of times 1. So there's our LOL, LOL, LOL. Now let's explain what just happened. All right. So, I'm sorry. Just giving it some separation here. So repeat, it takes in 2 parameters, the thing we want to repeat and the number of times it should repeat. We just saw that we're going to be using cons to repeat it. We know that cons requires as the final parameter to be a list. What does this guy say right here? When I've already repeated it all the times. Just boil down to the empty list, which will be the final empty list in my series of conses. Cons, LOL, onto whatever repeat returns for LOL number of times minus 1, which is going to boil down to a cons LOL onto whatever this guy returns for LOL and number of times minus 1, which is going to be cons LOL onto. Finally, we get down to our final call to repeat, which is just going to boil down to the empty list. That finishes that final cons. That make sense? Now, one thing I want you to pay attention to as we go and do some other examples is that this pattern here of doing something, especially since you imagine, since we're in a list-based language, we're going to spend a lot of time constructing lists, right? So it's going to be pretty common for us to have this pattern where we ask a question, ultimately finish off our construction with an empty list, otherwise do something else. That pattern is going to be a recurring theme for us. All right, so any questions on this and how this works? Go ahead.
So is Lambda a specific function right now? Like,
Well,
said function or Lambda is like an unnamed.
it's an unnamed function that we gave a name to. We used our define statement, which creates variables. We're creating a variable name repeat whose value is this lambda. So lambda in general is an unnamed function. So I can create 50 different kinds of functions using lambda. But this particular lambda, I need to call multiple times. And since I need to use it more than once, I've associated it with a variable name so that when I need to call it again, I can refer to it from within itself.
So we use the keyword Lambda to create it.
Correct, yeah. The keyword lambda creates a function. A lambda is an unnamed function. That function call, lambda, keyword, generates a function for us. Yep, yeah.
So because you're calling it in itself, there's no way you can do it without it.
No. It's 97.25% true. There's some interesting stuff with these things we're going to look at called lets and let recs and let stars that sort of kind of let you create an environment, but even then you'll be associating a name. So yeah, if you need to call it more than once, which is compatible with kind of our rules for variables, right? You know, you say, well, when do you put something in a variable? Well, if you need to use it more than once, you need to call it more than once, put it in a variable. So yeah. All right. Other questions on this? Kind of starting to make a little bit of sense. Okay, so what do we have here? You have your entire crash course on Scheme. We'll introduce a couple other functions here and there, but generally speaking, you now know how to define variables. You now know how to ask questions, and you know how to write functions. We will expand our asking questions things a little bit with something called a cond. In fact, why don't I go ahead and show it here? So we have something called a cond, which allows us to have a list of questions. So we can say greater than a 10, boil down to woot. Let's do greater than a 5, boil down to LOL. Greater than a 2, boil down to hello. Else, boil down to world, something like that. So this is kind of like a bunch of else ifs. Or if you worked with it before, I usually don't teach it in my programming classes because I just don't find it very helpful. Switch statement. So in some programming languages, you have something called a switch statement. I frankly think since you don't have to nest else's inside of ifs anymore, switch statements are kind of antiquated. In older languages like Pascal, you actually had to have break statements inside your switches to get, actually C works the same way, to get it to fall through, to get out. Otherwise it would have kept hitting other statements as it went down. Cond here will ask these guys in order. Only one of these can hit. So this works as kind of like an else, an if-else if. So this says, if this is true, do this. Else, if this is true, do this. Else, if this is true, do this. Otherwise, just do this. Okay, so it allows you, but if A is greater than 10, even though it's also greater than 5 and also greater than 2, it's only going to hit this one and be done. It doesn't, but you're going to find it helpful. Yeah, you could put it all on one line if you want, yeah. And you'll see that Dr. Rackett does indent for you, and most of the time it does a good job. Sometimes you'll find that it's actually, I would say all the time it does a good job. Sometimes you will need convincing that it's doing a good job. And sometimes when it does a weird job, it's because you forgot to close an extra parenthesis up above, and that's why it indented it at the wrong level than you were expecting. So sometimes it's kind of a helper when you kick it down a line. Yeah, but you'll definitely find it helpful to write your stuff on multiple lines rather than a single, collection of curly braces, or I'm sorry, of parentheses. Who's in charge of my parentheses? Noah. Noah's in charge of parentheses, the word parentheses. Jared, you're in charge of number of parentheses. Actually, in the past, this has happened, and this is for real. I don't want because you haven't even seen this gets so much worse than this. I had a student come into, they were actually having parenthesis-based nightmares. Like they were waking up in cold sweats. I think they were serious. Like it was funny to them, but also it happened. So I thought it was great. All right. I do miss Scheme. I haven't programmed in this in a while. This gives you that warm, fuzzy feeling, this language, doesn't it?
Sure.
You don't enjoy it already?
Not yet.
Not yet. It's like eating lit charcoal. All right. So let's look at a couple of things here. So I mentioned at the end of class last time, I was kind of rushing since I was already 10 minutes over, but Clancy didn't stop me. No, we're at 2:25. Okay. You're always allowed to tell me to shut up. I don't care, but I'll keep going. And if I'm in the, I really love Scheme. So if I'm just in the mood, I just keep going. We'll be here till midnight. All right. I one time had a grad class go 5 hours. One of my night classes are supposed to only go 4 hours. And I don't remember what happened. I think I know what it was. That week, for whatever reason, I think there was for the grad classes, we don't do it now because they're no longer at night, but Dr. Locklear and Dr. Wall, they like starting theirs at 5 and going till 9. I like my classes starting at 10 or 6 and going till 10 because there's more time on the golf course. But the class I was in, for some reason, started at 5, and I don't remember why. Maybe it was because it was one of their classes or scheduled funny or whatever it was. So I started at 5, but my classes ended at 10. So I just kept on trucking. And it was I think it was all students who had never had me before. It was international students, and they're really respectful. So they'll say a thing. I moved it to a 6 o'clock class, which helps them because, well, actually, it would hurt them now, but help them then. Because then they didn't have to come to campus so early, but we used to have the bus that would pick them up here to get them back home. But now the bus doesn't come to campus anymore because a lot of them live in Milwaukee or not here, not nearby. So now we have to do a ride share thing to get them home. All right, so anyways, I think near the end of class last time, I kind of quickly showed here's an example of the the language that is numbers. So we do want to a little bit redefine our idea of a language. I mean, we have this idea of a programming language, which we've already sort of defined as being anything that has facilities for remembering things, asking questions, and repetition, right? That's kind of my thing that I say all programming languages have that. But there are other things that are languages, like for instance, the alphabet is a language, right? The alphabet is what we use to construct English words, right? This is the language of the decimal numbers. This is maybe a little bit more tedious than it has to be, but close enough. Our numbers don't start with zeros, even though they could, right? Doesn't make it wrong if it starts with a 0, but somebody would say it was weird if you started and wrote a number starting it with a 0. So we could say our numbers all start with either a 1 through a 9 and then are followed by 0 or more 0 through 9s. So that's kind of what that says. That kind of concisely defines or describes a language. And you start reading through the first parts of the book, and it kind of looks like stereo instructions that are talking about inductively defined data sets and things like that. But ultimately, what they do is they come out the other end and say, "Oh, here's a convenient way you can describe a language through something called grammars, which are collections of productions, which ultimately describe a language." So, skipping through some of that fluff, this is a grammar called list of ints. All right, and this grammar has two separate productions. A list of ints can either be an empty list, or it can be an integer followed by another list of ints. Make sense? Now we can use our imagination and kind of think, what is a list of ints? So a list of ints could be an empty list. Could it be the list containing a 5? Could it be a list containing a 5 and then a 7? 5, 7, 13, so on and so forth. Or it can just be an empty list. Notice here that a list of ints, so it's a number followed by a list of ints, which could be the empty list. And if you're using cons to construct them, the empty list is just going to give you a plain list with just a number in it. All right, so this describes a pretty easy thing called list of ints that is just a list of integers, but this formally describes it for us. And we want to get used to looking at things like this because those things are, it's how we're going to be describing our more complex things as we get to them. And when we start writing our own language, how we're going to be defining our own syntax for things. Because we're going to purposely deviate from scheme syntax, still keeping it as a list-based thing. You can work with non-list based. Like we could create a language that kind of looks like Java in here, but it becomes complex enough that you start losing the learning of how our language is built. Thinking about, how do I implement recursion? How do I implement a variable environment? How do I write a for loop? Things like that. So it's easier to just do everything scheme style, but just say, oh, we're not allowed to use schemes built-in things, right? Instead, we'll create our own syntax for the stuff. So you'll see when we kind of get to that. But here's an example of a grammar that describes something pretty simple. Everybody's cool with that? You can read it? Okay, good. All right. Now, here's a couple of other ways that we can write that grammar. This is probably the one you're going to see most common. This guy right here. Secondarily, maybe this. So these are all the same things written. So this is, instead of repeating list of int twice, it just, this is fall through, right? So a list of int, it is either this or it's this. It's not a huge jump. This guy here, instead of putting them on top of each other, it uses the vertical bar as an or. It's this or it's this. Reads the same way. This guy down here uses something called Cleany star. All right, and this is a more convenient way of putting things when you say, I need 0 or more of something. So list of ints, concisely put, is a list containing 0 or more integers. That's what this says. If there's an asterisk, it's 0 or more. If it's a plus sign, it's at least 1. All right, all those make sense. We can read those, life goes on. Okay. So here is an S list. So an S list is a list of symbols. So instead of numbers, a symbol can be like ABC, it can be woot, LOL, hello. Those are all symbols. Okay. So an S list is a list of 0 or more symbols, which includes the empty list. Okay. Now we have something here called an S expression. An S expression is either just a symbol or it's an S list. So we have two different languages described here. One is the language of S lists, which is then part of the definition of this language of S expressions. Don't worry about what they're going to be used for, just this is what they are. All right, so we have something called an S list, which is a list of 0 or more symbols. And then we have something called an S expression, which is either just a symbol or it's an S list. Both of those qualify as an S expression. Either a symbol not being in a list or a list of symbols. All right, that makes some sense. Now, keep in mind here that an S list here is 0 or more S expressions, not just 0 or more symbols. So it can have just symbols in it, or it can have other S lists. So now this is saying an S list is actually a list containing symbols or S lists. So as you look down here, here's an example of a more complex S list, right? So this is something, this is a symbol, this is an S list, this is an S list, this is a S list, this is the end of that one, this is an S list, symbol, S list, symbol, end of an S list, S list, S list, symbol, end of an S list, symbol, end of an S list, end of an S list, end of an S list. Make sense? So now you have things that are S lists contained within S lists. That start sounding like recursion to you, Brocker? What about you, Noah? That starts sounding like recursion to you? Figured out how to unmute himself. All right, so remember that when you start thinking that, oh, I have an S list or I have something that also can have that same kind of something within it. Okay, because then we're gonna start seeing a new pattern of solving these problems where we say, well, how do I deal with an S list? Oh, well, you call your function that knows how to deal with S lists. But what if I have an S list inside of an S list? Well, you're gonna have to call that function twice, won't you? You know, that type of thing. We're building a tool that does something. All right, so another one. This kind of goes off something we dealt with. I'm just throwing you different examples of grammars here. So, you know, we dealt with binary trees last semester, right? So a binary tree is either an int, that would be a leaf node, right? Or it's a symbol with a left and a right subtree. Make sense? So if it's just an int, that's a leaf node. Otherwise, it's a tree. So a symbol followed by a left tree and a right tree. So here's some examples of trees. This is a tree, just a one. This is a tree. Here's a tree with a root node and 2 leaves. This is a tree with a root node, a left leaf, and then a right subtree with a root node and a left and a right leaf. So on and so forth. Make sense? Okay, so here are examples of things that meet this language requirement. All right, so far so good. All right, now we start getting a little bit more complex, and this is starting to describe, I'm going to call it right now, a simplified version of scheme. So we have a language of something called Lambda expressions. Where a Lambda calculus expression, the LC expression, can be one of 3 things. These are called productions. There are 3 productions currently available in our Lambda calculus expression. These will expand because this actually doesn't, in fact, you know, so we know what a lambda is already, right? What's a lambda? Unnamed function. Now, how many parameters do functions take? Does it have to be one? Yeah, it could be 0 or more parameters, right? This guy says it takes 1 parameter. Period. Just 1. Right, so this is our starter lambda calculus language. We're going to expand on this to be 0 or more eventually, but for right now, we're giving ourselves an easier to work with limited version of a lambda calculus expression. So a lambda calculus expression can either just be an identifier. When would you have, if you're thinking about programming languages, when would you just have an identifier? What does an identifier typically mean? Like, for instance, A would be an identifier, or cat would be an identifier. When we are looking at Java or C++ or Python and we just see A sitting there, what do we think that might be? Yeah, variable name. So this would be, later on, we're going to see this expanded out to be a var expression. This is a variable expression. If I just see an identifier sitting there, what do I have to do with? I got to resolve that. That has a value somewhere that I need to get in order to do whatever I'm doing. All right, so a lambda calculus expression in our starter mode here is either just an identifier or it's this list whose first element is the word lambda, who then has another list as its second element containing exactly one thing, an identifier. Not 0 things, not 0 or more, exactly 1. That's what this particular grammar says. And then the body of this function is another lambda calculus expression. Make sense? That's the second production. Third production is a lambda calculus expression followed by a lambda calculus expression. Identifier, or actually as it's written right now, probably a lambda with an identifier that is the single parameter to that lambda that will then give you an output. So this would be a lambda. This would be an identifier that has a value, or actually this might just be the value to bind to it. So I could have a lambda that takes in an A and boils down to an A, and I pass in a 5. So 5 gets passed in for A, and then it outputs a 5. So this doesn't give us a whole lot of flexibility for writing very complex programs, but this is a very simple starting point for lambda calculus expressions. All right, so here's a grammar that has 3 productions, and these are simple things, but should feel a little intimidating right now, mostly because of the word lambda. Don't you find when they start throwing Greek letters in there, Greek symbols, that things get a little, well, actually, at least they spell out lambda. They don't give you the lowercase lambda. That's a rough one, right? You just want to make you close the book and figure out, just go and take easier math, introduction to numbers or something. All right, so any questions on this at the top level? We can follow it. We don't know if we can work with it real great yet, but we get what it's saying. Okay. Okay, so this is, remember our buddy from Java, charat, which gives us a character at a particular bucket in a string? Well, we're going to write a function called listRef that gives us something that's a particular bucket in a list. All right, so I'm going to, so for example, if I gave it the list ABC and I asked you to give me bucket 1, it's going to give me, this is bucket 0, bucket 1, bucket 2, it gives me the B. All right, so we want to define listRef to be a lambda that's going to take in a list and a bucket num. And that guy should return the element in the list equal to bucket num. All right, take a couple minutes to write it. I'll give you 40 seconds. Give you like 4 minutes. Jeez. Oh yeah, name it like list ref 2 because it already exists in the language. Sorry about that. Or you can even call it char at if you want. All right, so let's take a look at this guy. Or we'll call it char at here. So this guy's going to take a list and a bucket number. And what we want to do is we want to get to the element of that list that has that bucket number. Now, when we can assume for right now that we don't give it an illegal value. We just assume it's, we have good input. But before you can just start writing code to solve a problem, you have to first understand the problem and understand the solution to the problem. So let's look at a couple of examples for this guy. So for instance, if I had A, B, C, and I said, give me bucket 1, what would I be looking at here? Well, what tools do I have to work with here? I know how to get the first element of a list, and I know how to get the rest of the list, right? So is 1 equal to 0? It's not. So let me call char at again on the cooter of the list and decrement that. So whenever this is 0, return the car. Otherwise, call the function again, passing it the coder of the list, and decrement this value by 1. That's our algorithm for solving this. So we'll ask the question. If bucket, or if equals bucket num 0 car list, else call char@, on the coder of list, and minus bucket num 1. So we're going to whittle our list down until we get a. So if I say call char@ on the list A, B, C, and give me bucket 1, that should give me the B. There's my B. If I say give me bucket 2, that should give me the C. If I say bucket 0, the very first time through, it says, ah, we're already here. Return the car. That should give me the A. Make sense? All right, so you had to break it down into, the tools that are laying in front of you. We solve all the problems in terms of the tools we have in front of us, and then we need to figure out the algorithm we're going to use. And we notice that once you see it, it looks pretty easy, right? The algorithm seems pretty simple, but until you get practice into thinking about things recursively, which we're not quite there yet, right? It's like, okay, well, I don't really want to call char@ again. I think I have to, but I don't want to. But we start seeing, well, how do I get a char@ something? Well, you call char@. That's the tool that does it. Just the fact that I currently am inside char@ just makes it seem more difficult. Like, okay, well, the char I'm currently looking at is not the char that I want. If I'm not here, that's not the char I want. So what do I need to do? Well, I'll whittle down my list a little bit, decrement my value, and just call my char@ again. That's the guy that knows how to get me the char@ something. All right, make some sense? All right. We'll talk about those next time. So for Tuesday, I have homework 1 up here, which is, this is actually from the book, but it's 3 different exercises. One's called duple, another one's invert, other one's down. I think you should have all the tools you need to do these. So you're going to be using the series of those. One thing I'll throw out there just in case you need it for one of these is I think I told you the function append last time, which glues 2 lists together. Understand that consing and appending do 2 different things. So if I just show you, I don't know that you'll use it. I haven't thought through it yet, but if you just look at, if I say cons 1 onto, well here, if I say cons the list 1 onto the list 2, I will get the list containing the list 1 followed by a 2. As opposed to append the list 1 onto the list 2, I will get the list 1, 2. Cons takes whatever this is and adds it as the first element of this list. Append concatenates these 2 lists together and reproduces a single list. All right, make sense? What I'll do is I'll just give you all this code from today just as a bunch of example stuff. I'll throw it on Slack. I'll put the homework assignment up here in a minute. But for Tuesday, do those 3 problems from, if you don't have the book yet, from the slides. Questions, comments, concerns, bribes? What about online? Any questions?
Not have anything.
Okay, well, I will see everybody on Tuesday. Code snippet thingy.
Actually, I do have a question, Professor. Super fast. I am kind of like in a pickle because I emailed you and everything, and I told you I had practice like around their time when class starts for soccer. I don't know if you got that or not, but they're